Okay, welcome everybody. So I'm just going to introduce Marty quickly. Marty Harvard is a professor emeritus of physics and former chair of the Department of Applied Science at New York University. His diverse academic background includes degrees in aeronautical engineering and astronautics, as well as work in sociology and economics. His present efforts focus on energy technologies that could stabilize climate change, including but not limited to space solar power. He's a member of the American Geophysical Union, the American Institute of Aeronautics and Astronautics, and he was elected Fellow of the American Association for the Advancement of Science. So without further ado, Professor Marty Harvard.
Thanks a lot, Kevin. It's a pleasure to be here. It's a pleasure to be here, one of my favorite premier institutions on the planet. Look, there's a lot I could be talking about, but time is limited, so let me just say this. The point of this talk, which is going to have some technical components to it, is motivated in a pretty straightforward way. We have a civilization on Earth with about 6 billion, and counting people. It's pretty old. It goes back 6,000 years. But if we're going to be able to continue to have a high-tech civilization on the planet, and you sitting in the audience being exemplars of that high-tech civilization, we are going to require a rapid, revolutionary transformation of the energy systems that run the Earth. The immediate problem is global warming. There are many other problems that humankind has: population, other resources, depletion, clear water, poverty, and so forth, inequality in the distribution of wealth. But all of these other problems that humankind has require stable and adequate sources of energy on a massive scale. Now, if we didn't have climate change, if we didn't have global warming to contend with, the conventional wisdom would have been coal. We've got oil and gas and coal, all of which were created over hundreds of millions of years, and we're using them up in a few hundred years. Coal is the most abundant, of course. But if we continue the path that we're on now, which is recarbonization, switching our electric power production from natural gas to coal, and essentially recarbonizing the energy supply, we have the capability of transforming the Earth's climate to back where it was 100 million years ago in the Middle Cretaceous, when both of the poles were deglaciated and sea level was 100 meters higher than it is today. I'm not going to dwell on this scenario. Global warming is an interesting and important problem, but the importance of it in this context is that it puts the need for an energy transformation away from a global system that's based on fossil fuel to the highest priority. Because if global warming constrains our use of fossil fuels, and fossil fuels have been the energy source of our civilization. I like to say we run on fossil fuels the way the Roman Empire ran on slavery. We need a way to get there. Now, the problem can be defined in an engineering sense, in a sense of, can we keep growing our energy use at 2% a year and GDP growth at 3% a year worldwide, and at the same time phase out all our fossil fuels by the middle of the century? That puts an enormous constraint on the energy system. And so I would like to look at the problem, although there's a more general talk that I give, and then I would be delighted to give, but I don't have the time, where we discuss a whole slew of alternatives. I would like to say that where are we going? What are the energy systems that might enable us to continue our high-tech civilization for hundreds, indeed thousands of years on the planet Earth? And there are very few. U-235 is limited as a nuclear fuel. U-238, from which you can make plutonium, has very severe environmental problems. Coal is limited, although it might be useful as a transition if we store the coal. We basically have renewable energy that is terrestrially based solar and wind power, and the wind power in orbit in space. And as a long shot, and we have to be honest that it is a long shot, controlled thermonuclear fusion. Now, one of the options, fusion, by the way, which is now funded by the world at $20 billion to build a test reactor that may not produce any electricity, being built in France, the option I'm talking about today, space solar power, has essentially very little funding or no funding. And I want to explore the possibility of getting a program going not only at the federal level, which is very important, but whether there's a role for entrepreneurs like yourselves. So without further ado, I'm going to skip a couple of slides. I do want to say that a number of agencies, of course, I don't believe in arguments from authority, but I'm going to make them anyway. A number of agencies from the National Academy of Science to most recently the Pentagon's National Security Space Office have supported the idea of solar power. This is from their recently released report, Space-Based Solar Power, and they make a number of recommendations, including government support for space solar power and encouraging the private sector to develop it, with perhaps the government backing up the risks associated with developing this baseload source of electricity. Space solar power is primarily worth developing because it can supply electricity at a baseload level. It isn't intermittent like wind and terrestrial solar. I'll get to that in a second. Just a general comment. Actually, I'm going to skip this comment. Just going to zip through this. If humankind continued to grow its energy consumption rate at 2% a year, the horizontal axis is years from now. The vertical axis is energy. They're both logarithmic scales. We would soon, within a few hundreds of years, be consuming all the energy that's incident on the Earth from the sun, which is 10,000 times more than our present energy use, and eventually much higher values. That's clearly non-sustainable. And I won't dwell on it at this point, except to say that we need to be targeting solar for one reason primarily, that it's one of the biggest numbers out there of continuously available energy, and it's more available in space than it is at the surface of the Earth. I'm going to skip this graph as well. Just a little bit on climate, because it does it is important. For the last 1,000 years, for the first 900 of those 1,000 years, the Earth's temperature has fluctuated, but something very extraordinary happened in the 20th century, particularly around the middle of the 20th century, where global temperatures began to rise. And that is, of course, no accident. It happened at the same time that the CO2 levels of the atmosphere were rising. And in accordance with predictions by various scientists, including myself, because I started working on this problem in the 70s when the Earth was still cooling, that we're generating this global greenhouse effect. And it is almost certainly driven by two factors: the use of fossil fuel, increasing energy use per capita, and the increasing population of the Earth, which has passed 6 billion recently and counting. Now, the idea of a solar power satellite, which goes back at least to the late 60s, early 70s, was proposed by Peter Glaser. Basically, I want to talk a little bit about the physics here. The design that was studied by NASA and the Department of Energy in the 1970s was a very large collector that would be placed in geostationary orbit. That's 40,000 kilometers above the Earth, 5 kilometers by 10 kilometers. And there would be a transmitting antenna 1 kilometer in diameter, beaming power to a receiver 10 by 13 kilometers in diameter at the surface of the Earth. Something this big. If any of you watched the Star Wars franchise on TV, I suspect from this crowd there might be a few. Think about the Borg ship. This would be something comparable to the size of one of the Borg battle cruisers. Why is it so big? Well, the reason it's so big is because of a law of physics associated with diffraction, the wavelength of microwave radiation. See, there are two windows through the atmosphere that you can see into space, and you can see from space to the Earth. There's the visible window where you can see, obviously, we can see the stars. We have eyes, actually, because the atmosphere is transparent. That's why a visual responses in the visible part of the spectrum. And the other part is in the microwave part of the spectrum, which is why radio astronomers put their telescopes on the Earth. And those are two windows through the atmosphere. In between, the atmosphere is pretty opaque. So transmitting the power that you collected in space at other frequencies would not be very effective. But these two frequencies are. And originally with space solar power, the basic idea was to use the microwave part of the spectrum. And a lot of people still want to use the microwave part of the spectrum. But the microwave wavelengths, which are 12 centimeters, are 100,000 times bigger than visible wavelengths, which are under a micron. And because of that, the spreading out of a beam is much lower because the beam will spread through an angle proportional to lambda over d, the ratio of the wavelength to the aperture. That's the reason why the original solar power satellite was so big. It didn't in itself have to do with the power. Once you have to make the transmitter and the receiver so big, you might as well put a lot of power through it because there's no point to doing it otherwise. And that forced upon you this humongous solar array in space, which is much bigger, in the original design, than all the solar panels that have already been manufactured, even with Google's generous help. That there's still a tremendous amount of area involved. Now, there's another idea that isn't normally even included in space solar power, but I want to include it because I want to make comparisons of different systems. And the idea would be, why don't we just build a power tower with mirrors that are 40,000 kilometers up in space? I mean, after all, if you could reflect solar energy, remember, the reason you go into geostationary orbit is because an object in geostationary orbit looks stationary relative to somebody on the Earth. That's why we have direct broadcast TV. And of course, direct broadcast TV is itself a kind of solar power satellite because we're collecting solar energy with photovoltaic cells, beaming it to the Earth. Now, the beam spreads out over a whole hemisphere, and it's only a tiny amount of power that's received by the 1 foot diameter dishes that you might have on your roof or something like that. But the principle is the same. If you could condense the beam and put it on a region that you want, and the solar power is almost continuously available in geostationary orbit. You're only in the Earth's shadow a very small fraction, maybe a half an hour a month. But suppose you just put mirrors in geostationary orbit. You just reflect the energy from mirrors onto the surface of the Earth, onto receivers. That way you would get 24 hours of sunlight, and it would be constant. Normally, photovoltaics are subject to the diurnal cycle. If you have flat plates on a roof, as you guys have out in your parking lot, it's not constant. Suppose you could, let's say you have an average flux out there of 200 watts per meter squared. I'm guessing, but that's probably right. In space, you would have 1,400 watts per meter squared. Suppose you could develop a transmitter that you could have those same photovoltaic arrays, and they would be getting 1,000 watts per meter squared continuously. Now, you guys can use it to charge up hypothetical electric cars, but I didn't see any plugged in before. But if they did exist, you could do it. But normally, people want the energy at times associated with the human circadian rhythm, like wanting to put on the lights at night. So that's the idea. Now, the space mirrors have their own laws of why things have to be big. Because in a space mirror, the problem is that the sun has a diameter of 1.5 million kilometers, and it's 150 million kilometers away. So elementary mathematics is that it subtends an angle of about 0.01 radians. And if you're 40,000 kilometers up in space in geostationary orbit, the spot size of the sun that you're going to project onto the Earth, because you preserve that divergence angle from Snell's law of reflection, is about 400 kilometers. That's huge. So even though you might have a lot of area of sunlight, it's going to be distributed over a long period of time. What is being shown in this interior panel is that the Russians already did a relevant experiment, the Zamadya satellite, which was basically you had astronauts in the Mir in its waning days supervising an experiment where a big plastic circle reflected sunlight onto the Earth. They did 2 experiments. One of them worked and the other one didn't deploy. But the one that worked, that was reported in the world press as a shining light with about the intensity of the moon moving across Europe was seen in many capitals. The reason it only had the intensity of the moon is the reason I gave you before. There's a great hit that you take on intensity because of the beam divergence. That doesn't mean we should rule it out for a planetary scale, but it has a big influence on what to do first in developing solar power, and that's what I'm really interested in. What's an evolutionary path for getting there? I'm not going to dwell on this, but I do want to say that there are some people who want to put things in space for different reasons associated with global warming than actually generating power. One idea is that there are various points, 5 of them, that co-rotate with the Earth as it goes around the sun. They're called Lagrangian Points. And one of those points, L1, the first Lagrangian point, always maintains, this is a point where if you put something, it stays there. Although you might have to stabilize it, it might not be stable at that point, but it's basically rotating around. So if you had something at L1, it would stay between the Earth and the sun as the Earth went around the sun. It might look like a big sunspot, but you'd have to make it very big. And calculations have been made, including by my colleague Ken Caldera of the Carnegie Global Ecology Institute, who's here right now, that show that if you compensated for the global warming of the Earth from burning fossil fuel, and mostly fossil fuel, to get to 12 terawatts, by a reflector in space that reflected a comparable amount of sunlight to the perturbation in the Earth's radiative energy balance that happened because of the global warming, you could neutralize the global warming, but it would have to be huge. And there was a talk, for example, given by this guy, Roger Angel. We have a cloud of randomly positioned flyers, 10,000 kilometers in diameter, blocking the sun. It's, again, a mega project, comparable to this Battlestar Galactica. Very interesting intellectually, but, not something that we're ready to do in 3 to 5 years. I'm going to talk about something that we can do in 3 to 5 years. I'm going to skip all of these curves, which are very interesting, but I don't have enough time. You guys should have asked me to give you a course, but that's another story. The question of cost comes up. This is a problem that has all sorts of considerations, from basic physics to economics to psychology to ergonomics to all sorts of things that come into it. But cost is a big factor, and normally people talk about the price of a solar module. How many dollars per kilowatt installed is one measure. And you can translate that into how many cents per kilowatt hour. And this is sort of a log-log curve of the dollars per kilowatt installed versus cumulative production. These are called learning by doing curves. It was developed in NREL, the National Renewable Energy Lab. And on this logarithmic scale, it comes down according to some power law. But it's not coming down fast enough to get to where we want it. Solar panels are still around $5,000 per kilowatt, or $5 a watt. But it's not a real watt. That's based on having an intensity of 1,000 watts per meter squared on a solar panel. That's the way it's calibrated when you want to know how much it costs. You never have 1,000 watts per meter squared, maybe once a day. You normally have much less, and the average is about 200 watts per meter squared. So solar panels are still pretty expensive when you compare it with, let's say, a coal-fired power plant, which is going to cost you $700 a kilowatt, or 70 cents, let's say, a watt. And we have to get down to that, or we are told by people in doing market economics, market fundamentalists, that that's the way the economics should work. That's another problem. I have a lot of problems with market fundamentalists. I'm not going to talk about that either yet. Terrestrial solar, which includes both wind and PV, both have this problem of intermittency. A lot of the things that I'm talking about actually are sort of frontline research activities, and people are working on them. Christina Archer, who's in the audience right now, just did a study of wind energy. Now, wind is very it's fluctuating. There are hour-to-hour variations in the output in a given location of a wind turbine. And so there's a question of whether you have to store the energy to make it a smooth power source. And we're talking about, remember, scaling up the renewable energy option to the point where it can power the world. We're looking at a different problem than a lot of people are looking at, which is, can you make any money out of solar energy by using net metering where you have the grid to back you up? The question is, what if renewables are the grid? What if we really want to have a steady state, sustainable civilization when we're not going to be using fossil fuel? Can we do it with renewables? And that's a totally different question. In the case of seasonal energy use, there's a mismatch in the case of wind because you normally, in the US, you have your peak demand coming in the summertime, and the minimum of the winds is also in the summertime. The maximum is in the wintertime. That's because the winds on Earth are driven by something called the thermal wind equation, which controls the jet stream, and it's why it took me an hour and a half longer to fly here from New York than to fly back. That's another story you're not going to hear much about. I want to say this, that Denmark, which is the world leader in wind electricity, has 20% penetration of their energy market, but they back up their intermittent winds with pumped storage. That's hydropower, where you pump it up in impoundment. And the reason they're able to do it is they're integrated with Norway, which is 100% hydro. We don't have that in the United States, so we would need some kind of storage, seasonal, or in the case of solar, diurnal, or even shorter for periods where we don't have solar. I'm going to skip this. There's some very interesting technologies for the storage of terrestrial, solar, and wind, the different talk. I do want to show this comparison of terrestrial versus space solar. The upper panel shows the solar energy available at some location. This one happens to be in the United Kingdom versus time of day in watts per meter squared. Versus the solar constant, 1,370 watts per square meter continuously in space. So the difference between the availability is very clear. You can see the seasonal differences from a June versus a December average and the nighttime average. So you can see the basic philosophy here is people say, what do we have to go to space? What's wrong with terrestrial, solar? We'll just build a lot of solar on the Earth. The basic point is there has to be terrestrial solar, and we very strongly advocate that. But for baseload power, the challenges for ground solar are in many ways harder than space-based power. The total solar energy at a typical site is much less than it is in space, and the energy varies widely with seasonality and daily. And baseload using ground solar requires a substantial overcapacity and costly large-scale energy storage, or global distribution networks like the global grid that Buckminster Fuller had envisioned at some point. I'm going to skip these. They're all very interesting, but I'm going to skip them and go to this, to these curves. I don't have a laser pointer, so just imagine that you see a dot moving around. That's red. It's a laser. We're going to end up with lasers. And I also apologize for the low contrast between the white writing. Actually, it doesn't even look white here. It looks like it's light blue. And the green background. That will be corrected in the next version. Marty Harvard 2.0 or something. We'll have that fixed. But I'm comparing three guys here. The three systems for conveying solar radiation to the Earth. In all cases, I'm assuming that the satellite is in geostationary orbit, not low Earth orbit. Geostationary orbit, 40,000 kilometers up, and that's the reason is that although we have looked at a lot of systems that use low Earth orbit, and they have a lot of advantages because if it's closer, the beam divergence doesn't spread the beam as much, and there are a lot of good things about it. The bad thing is that you have to constantly slew the beam and change its angle, and you take an enormous hit in the efficiency of the transmission of the energy. So all these are for space, so for collecting the energy in orbit. A simple mirror like the Russian experiment, except it can be multiplied hundreds of thousands of times in terms of the area if you wanted to do it that way, would spread its beam so that it would have 400 kilometers, or between 300 and 400 kilometers beam spot size on the Earth. Now, this might work if we wanted to power the whole Earth with mirrors, because you could work it out that if you put enough mirrors in space and they all were focused on this spot size, it could pretty much power the entire Earth. But it takes a huge capital investment to get there. The same thing in certain sense is true of microwaves. The original space solar power concept of the 70s, which had, remember, a 1 kilometer transmitting antenna and a receiver that was, I'm showing it here, is of order of 10 kilometers. And remember, this is governed by diffraction. The upper one is governed by geometric optics. That governs the spreading. For microwaves and lasers, geometric optics governs the spreading. That is, that the beam spreads proportional to the wavelength divided by the aperture size. So the microwaves, which have the big wavelengths, even if you have a big aperture, and this assumes a 1 kilometer aperture in space, the spot size is 10 kilometers. But if you do it with lasers, the laser has a wavelength of 1 micron or less, and even if the transmitter is small, in this case 80 centimeters, the spot size is relatively small. If you had an array of PV cells at the surface of the Earth, you could transmit to that array, a pre-existing array, and do that pretty efficiently. And actually, my son Eric and I have worked on this problem, and we have made a specific proposal to develop a geostationary satellite that would go up into space. It would take one payload of a conventional launcher, which exists, one metric ton payload. That's the size of the satellite. And it would deploy an ultralight photovoltaic array, perhaps an inflatable structure, and take that electricity and beam it through a 100 kilowatt solid state diode laser and to be received at the surface of the Earth. And that would be a very interesting demonstration. We think we could do that in a few years. The microwave guys, and there are microwave guys who want to do this experiment, and there are interesting microwave experiments to do with the International Space Station and so forth. I'm not going to focus on that now. Again, I don't have enough time. But I'm using this sort of as a reason for understanding that whatever we do should take advantage of and be cognizant of the underlying physics of the problem, because it should emerge naturally from the physics. If it doesn't, it's unlikely to be successful. Sometimes the physics helps you, sometimes it hurts you. Yes, I'm sorry to have kept going. Please, yeah.
If you use a concave mirror, can you get a smaller?
I don't think you can beat it, because if you can use a concave mirror, you can do that if it's if it's close by, if it's in the near field, you can probably do it. But if you're using, you're talking about the mirror, that will help you with the diffraction problem, but it won't really help you with the spot size problem. You can actually never get rid of the divergence of the sun angle between the two sides. Now, why that is something we could have a long discussion about. It would violate the second law of thermodynamics, because the heat that you would generate from the sun's rays on a surface can never be hotter than the surface of the sun that emits that energy. And the sun is like a black body at 6,000 degrees Kelvin. If you could eliminate that divergence, you could focus the sun's energy optically on a spot that would be hotter than the surface of the sun, and that would mean that heat was flowing from a cold surface to a hot surface. Anyway, it's a very interesting question. The answer is not obvious, and I would understand if you didn't believe it, but we should discuss that offline. Great question. What was the other question? Did you have another question? That was it. Okay.
Marty, is that true of lenses too? You can never use a lens and any lens.
Well, remember, when you're using a lens, you can converge the rays of the sun, but your focal distance is peanuts compared to the the distance. So the lenses are basically diffraction limited, whereas the mirrors are limited by geometric optics. The mirrors also are limited by diffraction, but the diffraction is a much smaller part of the problem than the beam spreading. The basic problem is that the sun is an extended luminous object. It's not a point. For a star to become a point, it has to become far enough away that the diffraction effect would overcome the geometric optics effect. And, okay, yeah.
In the laser option, what kind of energy efficiency do you have in the laser?
Okay, that's a good question too. Lasers were always thought to be very inefficient, but recently, probably thanks to a combination of consumer electronics and fiber optics and intense military interest, we now have diode lasers that have laboratory measured efficiencies of 50%. Now, normally lasers are around 2 or 3%, but the way the diode, I mean, these are electrically pumped diode lasers, so they're basically semiconductor sandwiches. They're like light-emitting diodes, but the light-emitting diode goes into a resonant optical cavity. And not only do we have those diode lasers at relatively high efficiency, but they can handle fairly high powers. In fact, I have a graph, I probably won't get to it because I'm very time limited, that DARPA recently had a competition to develop a 100 kilowatt laser for battlefield operation. Again, this gets into the whole question of why we spend huge amounts of money to kill each other, but we don't have enough money to survive as a civilization on a long-term basis. But actually, that's what's been driving our civilizations since World War II, has been all this money that's been pumped in mainly through the military, and that eventually spilled out into the civil sector. So we have these lasers. Anyway, I was getting to this. Northrop Grumman just built a factory in Redondo Beach, California, to mass produce 100 kilowatt lasers. They did this with DARPA funding. So we think we can get an existing off-the-shelf laser for an experiment like this. And I'll show you some pictures later on of ultralight photovoltaic arrays that could be deployed in space. Some of them would be inflatable. We think the technology to do this experiment is actually pretty doable in near term. And it would utilize surface photovoltaic cells that would already exist. And also the efficiency of conversion on the other end, on the surface end, would be very high, because photovoltaic cell efficiency is limited by the fact that if the cell has a single band gap, which characterizes the wavelength at which it absorbs a photon, then if a photon of exactly that wavelength hits it, it's absorbed with efficiency 1. If it's less than that, it doesn't absorb. If it's more than that, it absorbs that energy, but it rejects the other energy. And that's where the theoretical peak efficiency of PV cells of about 25% or whatever it is comes from for single band gap, because the solar spectrum isn't one frequency, it's distributed over a whole spectrum. Now with a laser, it is monochromatic. So you could set it up so to tune the laser to transmit at something close to the frequency of the band gap in the surface PV array and absorb that fairly efficiently. That, combined with the relatively more efficient PV, makes the laser feasible. You're still taking a big hit in transmitting the energy. The most efficient thing might still be to do it with just simple mirrors in space, except we just can't afford to build these 400-kilometer size arrays. And we can do this in the near term, and we might be able to do an experiment where, for example, we could beam energy to an African village, which is something I'd like to demonstrate, to run their light bulbs or to their computers, so that they could go onto the Google search engine or whatever it is. That's one of the reasons. Anyway, all these are really great questions. I'm going to try to finish up early, because I have a lot of stuff, but it's all basically variations on this theme. This is another laser idea. In this particular case, the laser beam is converging. Now, the reason you can do it is this is diffraction limited. It's really not image limited. We're using a laser This idea, by the way, was developed by Rod Hyde and Lowell Wood at Lawrence Livermore. These are guys who worked on laser, using lasers as anti-ballistic defense technologies. And of course, that never worked out. We spent hundreds of billions on it. But we did get the technology from it. And in this particular design, you know, the photovoltaic cells would absorb the photons. They would transmit through a fairly large lens. This would be a flat Fresnel lens, so it might be easy to manufacture it. And that could be beamed at spots on the Earth that would be relatively small. Again, each of these is a whole story in and of itself. There are experiments that have already been done at Mount Haleakala in Maui. And again, this was under SDI funding, where people have fired lasers through telescopic optics at satellites that were overflying. Here's an experiment on the left. This was the laser relay mirror experiment, where a laser was fired through telescopic optics. It also had adaptive optics. I won't dwell on that, but that compensates for the turbulence in the atmosphere. And a satellite was overflying it with a reflector. It hit the reflector, and the beam bounced back to another location on the surface of the island a few hundred kilometers away. And it continued to track the beam even as the satellite was moving. The idea was to demonstrate the pointing and tracking accuracy of laser beams. And with this kind of efficiency, we think we can do something like this from space, from geostationary orbit, which is basically motionless relative to the Earth. Here's some more hardware. People have built thin film structures with solar panels imprinted on them and actually tested them in space. I'm sorry for the distortion on this, but try to get your brains around it if possible. The upper panels show some of the technologies. What I'm basically trying to show is that this is existing technology, and that's why we want to focus on this for Space Solar Power Demonstrator. This is a group that's developed, a lot of these guys were working with the European Space Agency, but this is available technology, ultralight photovoltaic arrays in space. The metric here is how many kilowatts of power can you generate per kilogram, and you want that number to be high. So let's say I wanted to generate 300 kilowatts, just for the sake of argument, and if I could get 1 kilowatt per kilogram, that would weigh 300 kilograms. And I might still be able to get something that would be under 1 metric ton, even if I had a 50% efficiency or less than that with a laser. I might be able to deliver even 50 kilowatts at the surface of the Earth. That would be a very, very interesting experiment to do. I could probably do that with these arrays. There are still problems to be solved, like inflating them. The other question is, when we first proposed this, a lot of people said there is no 100 kilowatt laser that will do this job. But it turns out that those lasers were being developed by DARPA. And this is information that's available now, that this phase 3 program, Northrop Grumman, has actually built a factory in Redondo Beach to make diode lasers, 100 kilowatt diode lasers. And these are for battlefield operations. Eventually, they're going to perhaps, it is alleged, replace other kinds of weapons on the battlefield. Yes, sir. CW. 100 kilowatt CW. Well, it's a long story, but DARPA is actually known, for, when it works right, for delivering a new technology. CW means continuous wave, or continuous as opposed to pulse. Okay? Okay, let's. Oh, they'll probably have they'll be in tanks or something, you know. Yeah, I mean, these were not designed for solar power satellites. But after all, why is that different than any of the other technology that we got from the military? I mean, we didn't really, the military did not develop lasers so that we could have CDs. And music recorders. The military did not develop supercomputers so we could have really cool animated movies from computer graphics. It's basically because the military excites the part of our brain that triggers the fight or flee response, the amygdala, this little organ that's about the size of an almond that causes us irrationally to fear our enemies and write checks for a lot of money for people to do research. And then we take that and divert it to the peaceful functioning of our society. And that's basically the way our society works. And that's the big argument that I always have with classical market economists, because they think that what happens is that price signals will come into play, and that will cause people to invent things that will overcome the price signals. But in fact, you could show that almost none of the important technology that drives our civilization, from commercial aircraft to lasers to microwaves and solar and satellite telecommunications, and the internet, of course, which 30 years was supported by DARPA and NSF until the Wall Street Journal got a hold of it and said, look, at the market system works so well. So all right. Okay, this has to do with the costs of space transportation. Again, this has a lot. I want to have some discussion, so I'm going to actually go through this very fast. There are a lot of advanced technologies that could drop the cost of space transportation. The operative thing is this. The amount of energy that it takes to get into low Earth orbit is about 32 megajoules per kilogram. And it's about 60 megajoules per kilogram for geostationary orbit. That amount of energy is about the same order of magnitude, within a factor of 2, of the energy that it takes to fly a kilogram of mass from New York to Los Angeles on a commercial airliner. On the airliner, most of the energy goes to overcoming drag. If for the spacecraft, it mostly comes to supplying the kinetic energy of the orbit. But the costs are different by factors of thousands or tens of thousands. Why is that? There's nothing fundamental about that. Most transportation systems eventually stabilize around 3 or 4 times the cost of the energy to put them into place. And there are various ways that this might work. At the end of that rainbow is something called the space elevator, where you would actually have a tether that would be very long, that would be actually, it would not only be the length of geostationary orbit, but would go out way beyond geostationary orbit. And if you do the dynamical analysis, the forces that it would be acting on that cable would be pulling the cable towards the Earth below geo and pulling the cable away from the Earth, away from geo. But the cable has to be very strong, and it was pure science fiction until the development of carbon nanotubes, which are 200 times higher in their strength-to-weight ratio than steel. There might be problems that these nanotubes might be attacked by atmospheric chemistry, and there are a lot of other issues. But if you could do that, I mean, there's now a basis in engineering where you could build something like this. And the reason I bring it up is, I mean, that would tremendously reduce the cost of getting into space, because you basically ride up to space in an elevator, a kind of sky hook, where this, this rope would be coming down from heaven. And you would get on it, and you would ride up in an elevator. It would take you to geo. Once you're at geo, as Robert Anson Heinlein, one of the great science fiction writers of all time, said, geo is halfway to any place in the universe. And you could certainly build solar power satellites from there. But I'm not saying we should wait for solar power, for space elevators for solar power satellites. What I am saying is, if we start building an infrastructure in geo where we have lasers already, the space elevator concept is based on having these climbers that move up the cable, and they get their power from lasers. There are laser beams that are beaming power to them so that they can move up and bring construction materials. You could start doing that right away. They wouldn't have to be long enough to reach the Earth. They might just be a couple of kilometers in length, but you would already have the lasers in space, and you could begin to build an infrastructure in geostationary orbit that could eventually have be a space elevator, at the same time that you would begin to be building the infrastructure of space solar power. So my wonderful number one son Eric said, Dad, don't forget the slide that has to do with costs, because the people at Google are going to be very interested in the costs. I'm not sure that's true, but let's say it's true. Even today, you can do an analysis. Again, I don't have time to go through and justify it, but there are parameters that enter the analysis. The power per unit mass you can generate, the efficiency of the transmission through the atmosphere, the efficiency of storing the energy on the ground if you have a ground-based system, the intensity of the solar energy in space, the intensity on the ground, the capital cost of the photovoltaic cells in dollars per kilowatt in space and on the ground. If you put all of those together and do an analysis where you say, comparing the cost of ground-based solar with space-based solar, where the space-based solar costs are the costs of lifting something into orbit plus operating it there at a higher solar insolation versus the cost of building it on the Earth, but you have to pay for the storage. And it's primarily because solar PV is so damn expensive now that the lifting costs are a relatively small part of the whole thing. It's almost a break-in situation now at launch costs of $15,000 a kilogram, which you can buy launches to GEO on Russian and Chinese launchers right now. Now, we could go over this in more detail. Anyone who's interested, I could send you the talk. I could send you a white paper which elaborates on all of these numbers. But I want to actually end soon. I have a lot of wonderful stuff. But this is a study that was done by a group in the European Space Agency showing that you could supply the electrical demand curve of all of Europe with a solar power satellite based on lasers. And the energy would be collected in the Sahara Desert, where there's very little cloudiness. Excuse me. And it would be conveyed by high voltage DC power lines to Europe. And based on a number of assumptions that are built into the systems analysis, including those cost curves, the learning by doing curves, how PV costs will drop over time, the cost of space flight, all the parameter costs, this turns out to be an economically viable option. The question is, should Earth or space solar PV provide Europe's electricity by 2030? And these are very bold questions, and I agree that this whole concept is very bold, and maybe a lot of these assumptions are going to fall apart. But we can start working on this right now. I want to shut up because I only have a few minutes, and you guys probably have all sorts of things you want to criticize about this. But I'm going to stop now.
Marty, I have a question.
Yeah.
Is anybody in the world doing this? Japan?
Yeah. Both Japan and Europe have small budgets for looking at solar power satellites. Did you want to address that, Paul? Because Paul is one of the authors, by the way, Lieutenant Colonel, who is one of the authors of the the National Strategic Space Office study on space-based power, which was fairly positive about solar power. And maybe you would like to answer that question?
The Japanese have a lot of interest in it. They have interest in putting it on the International Space Station as a demonstrator. The Indians. Thank you.
Thanks. The Indian government has offered up some money to pursue some demonstrators. The Russians have shown some interest, and then various other countries. So we have indications that they are interested in it.
So all those countries are investing money, but the U.S. is not.
Small amounts of money, very small amounts. I mean, this is in
but
the
the
very,
U.S. isn't
very
even
early
investing
stages.
a small amount of money.
Yeah, compared to nothing on our end.
I'm sorry, yes.
Hi. So I have a couple questions.
Sure.
One is, so what are the reality problems of heat rejection and stability control for a laser-based inflatable solar deployed solution? That's one question, and how you deal with those. And the other question is, how does this solution for a geo-based solar collector transmitter compare to something like a lunar-based solar collector?
Those are great questions. First of all, I'm not going to be able to answer the question in detail, but I think the important thing is to make sure that everyone understands the issue. Maintaining the stability of the lasers. After all, lasers are very tricky things, and they have optical cavities and everything. And they have these lasers, by the way, that Northrop Grumman is building have to be stable under battlefield conditions with bombs going off and everything. So, assuming they can match their specs, that I think that would be certainly a step in the right direction.
Yeah, but they're not attached to a large inflatable structures.
Yeah, well, now, okay, I never said this was easy, and I can't guarantee it's going to work. But I do think that there's enough plausibility to start working on it. The heat rejection problem is an issue. You're going to have to build solar radiators that are going to dissipate the excess heat, and there's a lot of room for ingenuity in engineering design on that. I'm sorry, you had another question too?
Oh, the other question was just how do you feel that the solution of a lunar-based power?
Okay, yeah. Well, actually, one of the inventors of that, Dave Criswell, is a friend of mine, and we've been talking about this for years. The lunar power satellite has the advantage. This is like a solar power satellite, but you build it on the moon. And you don't have to build a satellite because the moon is already there, and you have two transmitting stations on the two different limbs of the moon. It's based on microwaves, and you use the materials on the moon because the moon has silica, and you have to build a manufacturing base to do it on the moon. My attitude about that is, I think it's very imaginative, and maybe it's going to happen someday. And I think we have to continue research. When NASA goes back to the moon, I think they should certainly continue to do the materials science research. Even if we don't build a lunar power satellite where the satellite is 400,000 kilometers away, we might want to use lunar materials. I mean, Arthur C. Clarke back in the 1960s figured out that, you only need 1/60th of the energy to get something to geostationary orbit from the moon that you have to get it from the Earth's gravitational potential well. So why don't you build an electromagnetic mass launcher? And at one point, NASA did have research going on in materials science, trying to build photovoltaic cells out of the materials of the moon. It's very important. I tried to focus this talk on an immediate next step experimentally. This is not the last word, but it might be the first word, and it might help to galvanize sufficient interest to continue the program. There are a lot of ways. We talk a lot about how to jumpstart space solar power. There's another idea, just to create an X Prize for wireless power transmission. And again, I don't have all the time to elaborate that. I just want to give you guys a taste of what we are thinking about.
So guys, unfortunately, we're out of time. We can continue questions in Madrid afterwards. We have that room booked, but we have to clear out for another group.
Can I just 2 minutes to just wrap up real quick?
Sure.
It'll be real fast.
So they can wait.
I just wanted to make a plug. Eric, you're already made an allusion to the report here. This is from the National Security Space Office. We looked at space solar power as the strategic implications of it. We looked at space solar power from the strategic implications. Can we enable space solar power as a way for us to avoid resource conflicts in the future and to enable the United States as a energy exporter instead of importer? So I'd invite you to take a look at the report. It's on the National Space Society's website. That's nss.org. You have to I'm not exactly sure where the link is, but it's fairly prominent on their webpage. But it gives you a fairly good primer on space solar power. It's not nearly as technical as this, but it gives you a very wide base as to, and two of the things that the report is advocating is that we need to do continued studies on this, and we need to do demonstrators. But right now, space solar power doesn't have a home. It doesn't fall within the DoD's realm. We just did this as a quick look study. It doesn't necessarily fall under DOE, Department of Energy. It doesn't necessarily fall within NASA. So we are looking for a place for space solar power to have a home and to continue the efforts. Next 2 minutes.
Thanks.
Thanks.